Okay, great.
Do you mind if I record?
No, you can record it. Yeah.
Okay.
Just gonna. Ashley, do you want me to share my screen, or do you want to share? What do you prefer?
Because I'll probably somehow find a way to mess it up.
Okay, confidence. I love it. Let's try this then. Can everyone see this?
Yep.
Okay. Oh, whoops. Starting from the wrong part here. Present for free. Okay. Hi, the two of you. Today, we're going to present our findings on cellulose-based biomimetic skins. So biomimetic skins enable a wide range of medical and performative functions that change how we interact with the world. Their evolution began in 1974 with the manufacturing of the first prosthetic hand that included sensors, and has since progressed to the flexible electronically active polymers we see today. And as the field of cybernetics has expanded, the necessity for biocompatible electronics has become increasingly clear, bringing biopolymers to the forefront. So herein we examine the use of one such biopolymer, cellulose, for its use in electronic skins. So as the largest organ in the human body, skin plays many roles. It is self-healable. It's a self-healable barrier against external stressors, a tactile sensor, and body temperature, peripheral circulation, influence, balance regulator. So we're going to begin with a quick refresher on the skin's structure and function so we can determine which properties are most important to replicate in future e-skins. So I chose these two figures. One of them is the three principal layers of the skin on the left and their subdivisions. And then the second one outlines the principal neurons responsible for the afferent signals of our somatosensory system. So mechanical and electronic properties are the two most important properties to consider in designing the human-machine interface. And we always seek to replicate their function through biocompatible mechanisms. So these are the two systems that we're gonna dive into. First, the skin delivers the aforementioned functionalities through its intricate anatomy. So capillary blood vessels, lymphatic vessels, peripheral nerves, and sweat glands are densely distributed amongst the three different layers of the skin, which are the epidermis, dermis, and hypodermis. So the outermost layer of the skin is heavily furrowed and made up of densely packed hexagonal cell structures called corneocytes that give it the suppleness to flex and move upon extension and contraction. And its mechanical durability is largely due to the tight cell junctions between these cells. Then these are formed by desmosomes, which are just cell adhesion molecules. From an electronic standpoint, these furrows and ridges are also critical in concentrating force and sometimes discerning minute tactile signals, such as texture. And these are mostly in the palms of our hands. Moreover, this layer contains free nerve endings for temperature transduction. However, extensibility and conductivity are dependent on the skin's moisture content. So higher moisture, the more conductive, well, actually not higher moisture, but the optimal moisture, it has good conductivity and extensibility. The dermis provides the greatest mechanical strength to the skin. It comprises of two layers, the papillary and reticular dermis. The former is most important in resisting shear forces and is made up of vertically oriented, loosely distributed small collagen and elastin fibers, as well as capillaries and veins that supply the epidermis with nutrients. It also contains some neurons, mostly in the dermal epidermal junction that include nociceptors, which are pain receptors, thermoreceptors, and light touch mechanosensors. So because they're shallow underneath the surface of the skin, they are for the lighter touch. In the reticular dermis, fibers are larger and oriented horizontally, allowing the organ to extend, On average, biological skin is stretchable up to 75% strain. So upon contraction, there's an amorphous ground substance as well that displaces laterally to prevent tears under high pressure, and the elastic fiber network ensures complete recovery following deformation. Finally, the hypodermis is a subcutaneous adipose and connective tissue layer that acts as a gliding layer that allows for uniform movement of the dermis in epidermis. It's an insulator and an energy source as well. It is intertwined with the dermis through nerves and vascular networks, and principally comprises of lipid-filled cells, giving it the ability to attenuate and disperse applied forces and protect the skin from, the skin and underlying muscle from excess trauma. There you go. Next, we'll look at the somatosensory system. So the somatosensory system serves three main functions: exteroception, which is perception of external stimuli; interoception, which is perception of internal stimuli; and proprioception, which is perception and control of body position and balance. So it does so through three principal types of receptors: nociceptors, thermoreceptors, and mechanoreceptors. So again, nociceptors are pain receptors, thermoreceptors for temperature, and mechanoreceptors obviously for touch. So the perception of temperature, humidity, vibration, and haptics is felt on account of rapid ion transport between epidermal neurons. Each receptor measures force over a unique time scale, receptive field size, and mechanical threshold, and sends information via different sensory neurons. Therefore, receptor function is divided into a variety of categories, including slow adapting, dynamic, static, as well as low and high sensitivity and selectivity. So upon stimulation, information is recorded as the time between voltage spikes, called action potentials. Throwback to Science 10. And these are created through the opening of ion channels. A stimuli will elicit a response from a variety of receptors, resulting in a series of afferent neurons, each containing info from many different receptors, signaling the central nervous system. So the combination of input from these receptors is interpreted by the brain to give complex information about various sensations. And as previously mentioned, the mechanical properties of the skin have important effects on its sensory characteristics. Owing to its softness and compliance, skin adapts to the surface of an object, altering the distribution of forces on mechanoreceptors, providing more contact area for sensory perception, and improving grasp through friction. Ridges are also useful in concentrating force and discerning differences in texture, slip, and hardness. So ultimately, the human skin is a multifunctional, high-density sensor array. So tactile perception relies on a large array of sensors and neural pathways that are spread throughout the body in a non-homogeneous, function-specific manner. So sensory receptors are morphologically specialized to transduce specific forms of energy, and each receptor has a specialized anatomical region where stimulus transduction occurs. Most receptors are optimally selective for a single type of stimulus energy. And this figure is an example of various mechanosensory field receptor sizes, so receptive field sizes, and mechanical thresholds. And on the right is all of our nociceptors and mechanoreceptors. And then also at the bottom, we're talking about proprioception when they with the muscle and skeletal mechanoreceptors. All right. When building a biomimetic skin, we therefore must consider not only the sensing, but signal encoding, transmission, and conveyance to the central nervous system. So once a specific sensation is sensed by a biomimetic skin sensor, how is that transduced to the brain and properly interpreted? So we'll get into that in the next section, but essentially, based on the intrinsic mechanical and electronic characteristics of skin, a true biomimetic skin should be flexible, compliant, and soft, yet tough and durable. It must be porous, yet insulating, and it must have good biocompatibility, biodegradability, and self-healing capabilities. Electronically, it must be self-powering, and the minimum requirements for tactile sensory perception include normal force sensing for grasp control, object manipulation and orientation determination, tensile strain monitoring for proprioception, shear force sensing for grasp control and friction determination, vibration detection, and vibration detection for slip detection and texture determination. But the possibilities are endless. Future e-skins may even be able to selectively enhance some of these properties, increase mechanical strength without sacrificing pliability. So it can be tear-proof and potentially act as a freeze or fire-proof protective layer. All right, so now we'll get into how we can blend these electronics with the human body and how these sensors signal the central nervous system. So first, we'll talk about how to mimic skin mechanics. So ultimately, we are looking to build devices with high flexibility that can conform to the curvilinear and dynamic nature of the skin. This is accomplished through polymer microelectromechanical systems, thin film transistor matrices, and the reduction of thickness of current electronic devices. So if we can recall, mechanics directly affect sensory abilities, therefore materials must have low elastic moduli in all structural planes. So there are three main strategies for achieving electronic devices with enhanced flexibility. There's buckling, discontinuous rigid components, and intrinsically stretchable materials. So the first one, sorry, just gonna grab some water here. Sorry, okay. The first is achieved by mounting a flexible device onto a pre-stretched elastomer substrate. So once it returns to its original unstrained position, the flexible device buckles out of the plane of deformation. So this offers super high mobility. So it's used for places that would require it, like joints. So you can think of your knuckles when you think of the buckling effect. Second one, discontinuous stiff components, are when electronically active stiff moieties are patterned throughout an elastomeric substrate, so connecting through buckled or intrinsically flexible conductive materials, but they are rigid, usually inorganic components. And the final strategy, intrinsically stretchable materials. It seems like the most evident one, but the performance and fabrication process of these materials are not yet sufficient for the types of circuits required to process biomimetic signals. However, it is simply materials with intrinsically suitable mechanical and electronic properties, such as elastomeric and conductively active blends. Next, we'll look at how we can mimic skin sensation. So this is a bit of a text-heavy slide, sorry about that, but there are 4 general types of receptors that are utilized to mimic the sensory capabilities of skin, including static force, static strain, dynamic force, and thermal transduction. So the first type of sensor is a capacitor, which functions to mimic static force and strain, or slow adapting receptors 1 and 2. So when a pressure is applied, distance between electrodes or electrode overlap changes, which will result in a fluctuation in charge or capacitance. So this change in electric potential is then transduced in methods that we'll discuss in the next slide. The second type of sensor is a piezo-resistive sensor, which functions to mimic static force and strain, as well as thermoreception through a specialty sensor called a resistance thermometer. So they have inherent temperature sensitivity. Therefore, these sensors, if you'd like to use resistive sensors that are purely for force transduction applications, then we'll usually stick to contact resistive sensors. So essentially, resistive sensors, both of them, they function through 2 mechanisms based on the principle that resistance is equal to resistivity multiplied by length over cross-sectional area. So the first mechanism utilized by piezo-resistive units is due to a change in resistivity caused by the deformation of semiconductor band structures and percolation pathways between conductive particles. And the percolation pathways are just the conductive pathways. The second mechanism utilized by contact resistive sensors is due to a change in geometry. So when a pressure is applied, the device is stretched, increasing length and decreasing contact area. And both of these, both piezo-resistive sensors and contact resistive sensors, when that stress is applied, will result in an increase in resistance, which is again transduced by methods we'll look at in the following slide. And then finally, there's piezoelectric or triboelectric sensors, which are employed to mimic dynamic sensations. So the application of mechanical force to these materials results in the production of energy or voltage due to a change in the intrinsic orientation and therefore magnitude of the dipoles within the active layer. This in turn creates a small voltage. So the generation of energy upon mechanical deformation gives them the advantage of self-power. And it has been shown that vertical pillars of these materials can allow for arrays of much higher density and therefore sensitivity than human skin. So once a sensor produces a signal, this signal is converted to pulse-like waveforms that mimic action potentials through amplifiers, oscillators, and sometimes edge detectors. Edge detectors are usually required for optogenetic stimulation though. To enhance spatio-temporal resolution, transistors are coupled with each sensor. This avoids the issue of having to reduce the size of sensors in order to accommodate a high density array, which would in turn reduce the amplitude of analog signals, such as capacitance or current, and increase crosstalk. So crosstalk is when signals get mixed up between sensors. The digital output signal can now be utilized to stimulate neural interfaces through three main mechanisms: electrical, optogenetic, and magnetic. So in the former, peripheral neurons are stimulated through electrodes. Obviously, electrodes that can target individual neurons are more attractive as they enhance localization and specification of stimulation. Optogenetic stimulation is not really something I fully understand, but from what I do understand, it is essentially reliant on light-sensitive proteins that are introduced to target neurons of the somatosensory cortex in the brain, which are triggered by light stimuli. So interpreting the sensations generated through this mechanism is a learning process. And to this point, it has only really occurred in animals, as far as I know, not humans. That's what I mean. And then the final stimulation mechanism is magnetic stimulation, which simply employs coils that can be integrated into our electronic biomimetic skin devices as magnetic generators that remain in contact with the skin. And then upon stimulation, the coil generates a magnetic field that penetrates the skin barrier and induces an electric current that activates neurons. So that's how we transduce. Next, we'll look at the human-machine interface. So from a physical standpoint, there are two principal interfacial issues in designing on-skin electronics: conformability and adhesion. So not only are these properties important in ensuring longevity and robustness of the device, but optimal conformability and adhesion play a large role in the electronic coupling between electrodes and skin. So as seen in the figure here, oh, it's a little blurry, sorry about that. In figure 2 of the figure, we can see that low compliance creates gaps at the coupling interface, resulting in higher interfacial impedance. So the weaker the capacitive coupling of electronic and ionic current, the more noise or less sensitive, basically, and selective the device. So ideally, compliance is high and interfacial impedance is therefore low, allowing ionic fluxes to transduce efficiently across the skin barrier. So as we've seen, prolonged intimate contact with the dermal layer is difficult to maintain due to its stretchability, or its stretchable and hydrophobic nature, as well as frequent dynamic deformation. Therefore, conformability is achieved by matching mechanical properties the device to the skin at the specific point of contact. And the second issue, adhesion, has been solved through the use of naturally self-adhesive materials, ultra-thin sensors, and biologically inspired architecture, such as suction cups of octopi, microneedles of endoparasites, etc. The bottom picture here is just a self-adhesive test of a carbon nanofiber blended material on different substrates. The most important property to consider when blending or building a cybernetic device is its biocompatibility. Without it, device performance is compromised. Biocompatibility is difficult to define, as all biomaterials elicit a different response depending on the tissue and environment. The idea of ubiquitous biocompatible material remains theoretical at this point. However, we can define biocompatibility based on the tissue's response. So this response can be one of four things: toxic, bioinert, bioactive, and bioresorbable. So in the case of e-skins and many other cybernetic devices, bioactivity is the goal, of course. This response indicates an intimate connection is formed with the host tissue. So how can we maximize this connection without sacrificing device performance? Biopolymers, and in this case, more specifically, cellulose. So this section, we're just going to look at why and how it is utilized in electronic skins. Okay, I must have forgot to add my photo here. Sorry about that. But in general, natural biopolymers provide unique merits such as good biocompatibility or even biodegradability, natural abundance, and sustainability, which makes them promising building blocks for biocompatible conductors in green electronics. These properties are essential for the long-term use of on-skin bioelectronics. Cellulose in particular has superior structural properties, high tunability, and biocompatibility, and thus has been used extensively to endow conductively active materials with high compliance and flexibility to mimic the mechanical properties of and facilitate the blending of electronics with human skin. So we'll get into a few of these advantages now. So just to begin, the structure of cellulose, it is a biopolymer made up of a linear glucose chain connected through 1,4-beta linkages. This means that hydroxyl groups at C2, C3, and C6 are free to participate in hydrogen bonding, endowing the material with various crystalline structures and functionalization capacity. Furthermore, there are two ends, the non-reducing end where anomeric carbon is in a glycosidic linkage, and the reducing end where the anomeric carbon is free to take on aldehyde functionalization. Intramolecular bonding occurs between, or principally, between C3 hydroxyl groups and the other free hydroxyl groups C2 and C6. And together with glycosidic linkages, these influence cellulose rigidity and the tendency of cellulose to crystallize or form fibrillar structures. There are many forms of cellulose depending on the state of intermolecular bonds, two of which are pictured in the lower picture here. So cellulose 1, or native cellulose, is the top one. It's A. Intermolecular hydrogen bonding occurs between C3 hydroxyl and C6 hydroxyl primarily, causing the biopolymer to layer along with hydrophobic. Sorry. I did mess up my script, but I believe it's just lower, it's just lower crystallinity than cellulose 2, where intermolecular bonding occurs between C2 OH or C2 hydroxyl groups and C6 hydroxyl groups primarily, causing intermolecular bonding with C2 hydroxyl to be avoided in lieu of C2 intermolecular bonding. So that makes cellulose 2 more densely packed through stronger interconnections and therefore more crystalline. There are many different ways that that hydrogen bonds link between cellulose structures. I'm not sure how many exactly, but there's a lot of different crystalline structures that can take place. Intramolecular hydrogen bonding provides us with the ability to tune porosity and crystallinity of cellulose-based materials, giving a wide range of micromorphologies, such as cellulose nanofibers, cellulose nanocrystals, bacterial cellulose, which I guess we're not really tuning actually, and cellulose nanosheets. However, they can severely limit solubility. So hydrogen bonding can severely limit solubility, making these materials difficult to work with and reduce reactivity of hydroxyl groups and possibly enhance crystallinity and therefore rigidity of materials when that's not what we want to do. We would like them to be more flexible. Plants are the main source of cellulose and also why it is the most abundant biopolymer on Earth. So the nanostructure of a plant wall is a robust assembly of three primary biopolymers: cellulose, which is present as a semi-crystalline elementary fibril, hemicellulose, which acts to decorate and cross-link elementary fibrils and facilitate interactions with lignin, and lignin, which is an amorphous polymer that associates closely with hemicellulose. So natural cellulose can be transformed into micro and nanoscale materials by applying specific top-down or bottom-up approaches, yielding defined products such as the ones that we've already mentioned, but the three main ones are cellulose nanocrystals, cellulose nanofibers, and bacterial cellulose, which is actually a bottom-up approach because it's synthesized by bacteria. So compared with plant cellulose, bacterial cellulose is very pure. It contains no hemicellulose or lignin and only a very low amount of carbonyl and carboxyl moieties. It possesses the highest crystallinity, excellent water absorption capacity, and extraordinary mechanical strength. And then between cellulose nanocrystals and cellulose nanofibers, the crystals have much higher aspect ratio and crystallinity, and the fibers have a semi-crystalline structure that provide them with increased flexibility and stability and stable thermal properties for use in flexible electronics. So these are just some of the, these are just two images of the differences between the different micromorphologies of cellulose. So on the left, we're looking at the difference between nanocrystals and nanofibers. And it also mentions some of the top-down approaches or methods of breaking down native cellulose that will help us achieve the desired morphology. And then on the right, we have different morphologies of cellulose prepared by different methods. So although it is not naturally conductive, cellulose is or has been shown to be intrinsically piezoelectric and dielectric. So as we mentioned with the sensor slide, piezoelectricity is often used as a sensor property in for dynamic sensing, and dielectrics can be used in capacitors and capacitive sensing, And both of these properties, in this case, directly relate to the state of hydrogen bonding and aspect ratio of the nanocellulose derivative. They're both based on the material's polarizability in face of mechanical stressors or an electric field. So to endow conductivity, a number of modifications can occur through surface hydroxyl groups, as we'll see on the following slide. So these are some of the different chemical modifications employed to enhance hydrophilicity and hydrophobicity on the left and right, respectively, or they can simply enable polymerization and blending with electronically favorable material. And once functionalized or not functionalized, it can just occur with the hydroxyl groups. We can polymerize through grafting to, grafting from, and grafting through methods to create blended materials with optimal mechanical and electronic properties due to their high tunability Cellulose nanomaterials can be used to construct specifically structured materials with different forms, such as fibers, films, papers, aerogels, and hydrogels, some of which you'll see in the following sections. So I will let Ashley take it away if she wants.
Okay. Okay. Yeah. So I'm just going to be going over a bit of the applications of some electronic skins. Yeah. Thanks. Okay. So electronic skin is commonly used in both the medical and the performative sides of the fence. It is widely used in healthcare applications because they can be used for continuous real-time monitoring of human signals. So one of the things it is commonly used for is to monitor tissue pressure. This includes information about the arterial pulse and blood pressure when relating it to human activity. This is actually pretty important because it's good for early diagnosis of a cardiovascular disease, as a constant fluctuation within one's blood pressure could actually lead to signs of heart attack, stroke, or different arterial blockages. So with long-term measuring of this, hypertension, cardiovascular, and other cerebrovascular diseases can actually be prevented. These skins are also used in the medical field for measuring body motion, temperature and humidity, metabolites, electrolytes, and other disease biomarkers. Due to its non-invasive real-time dynamic therapy, there has actually been an increased need for transdermal drug delivery as an alternative to traditional injections or oral intakes. Aside from the many uses it has within the medical field, these electronic skins are also useful in other aspects. One example is giving people with prosthetics the feeling back. Although they will still obviously have a prosthetic, the electronic skin built with some specific sensors can actually give them that sensation. So they can then detect pressure or even pain through their prosthetic to help them kind of have more of like a quote unquote normal life. These skins are also in testing to be used to help give robots feelings. So they are more human-like. This is widely thought to help in future developments for any robots that might be used within movies, so that ultimately they could like act better. So it would help ensure like a better movie is ultimately made in the end. You can switch the slide. Okay, so there are three main types of sensors incorporated into these electronic skins to help better provide data based upon what the overall application of the skin is. So the first type of sensor is a physical sensor. These sensors are one of the key building blocks of electronic skins. Typical physical sensors include mechanical sensors such as resistive type, capacitive type, piezoelectric type, or triboelectric type sensors that Kirsten had mentioned earlier. These also include resistance type, thermistors, I always mess that word out, pyroelectric type, and thermoelectric type. Humidity sensors are also used, which can include resistive, capacitive, and triboelectric, much like the mechanical sensors, but they also include hydroelectric generators. Within those sensors, there are also multifunctional physical sensors such as self-healable and implantable. The second type of sensor is electronic. The sensor is used to measure any action potentials within the tissues of the body. They're commonly used for measuring ECGs, EMGs, and EEGs, as well as any other detection of the heart, neural, or neuromuscular diseases, including Parkinson's or Bell's palsy. Those sensors actually use traditional metallic electrodes as well as conducting gel. And then the third type of sensor is chemical, which is used to monitor biomarkers within the body. An example of this is measuring the amount of sugar within one's body to help with diabetic patients. It is also used to measure respiratory diseases and other epidermal stimulations, such as the iontophoresis-based sweat sensor, which is actually used to extract sweat samples for the diagnosis of cystic fibrosis or for other drug analysis. The next slide. Thanks. Okay, so I'm just going to go over a couple different like articles that kind of show where we are currently with these sensors. So the first article is entitled Smart Cellulose-Based Electronic Skin with Humidity-Driven Dynamic Performance. So in February 2020, we'll briefly look into the production of a humidity-driven gel-derived cellulose-based electronic skin. Say that 10 times fast. A cellulose-based gel was ultimately created, which demonstrates reversible and tunable features of viscoelasticity, self-healing, and ionic conductivity, which ultimately makes it useful for electronic skin or the actual electronic sensors. So due to the right hydrogen bonding between the cellulose and the ionic liquids, it can disperse homogeneously, while the fraction of water within the dispersion of the hydrogel can actually be regulated. So since the hydration state of the dynamic gel can be regulated by humidity, it allows the mechanical performance to switch between rigid and flexible states. It was tested that water will actually expand the hydrogel volume, which provides ion migration channels. This is ultimately responsible for the self-healing property. This gel with all these properties actually matches the overall demand of the electronic skin. So it basically confirms that the gels in the skins are useful, especially within those medical applications. The picture that you can see on the left is just an example of one of the cellulose gels. It's kind of like really big and like really weird. And then the picture on the right kind of shows a bit more of like the structure between the rigid and the flexibility states. So when you're adding in the water, it would be towards the right, whereas the ones on the left are actually with less water added. So you can see the ones on the left do have less hydrogen bonding, so it's more weak, whereas the one on the right is like, it has more water, so it has a higher mobility. Next, please. Okay, so the second paper that I'm going to be talking about is called Recent Advances in Cellulose-Based Membranes for Their Sensing Applications. So we're just going to jump a little bit forward to September 2020, where we'll actually look into a deeper study of like different sensors used. The paper actually summarizes the recent progress of the cellulose membranes as sensors while talking about their preparation, properties, as well as prospective challenges. It does go through pressure and strain sensors, temperature sensors, chemical sensors, and biosensors with a bunch of like subcategories underneath as well. But just to kind of keep things like less complicating, I'm just going to focus on one of them. So I'm just going to talk about the pressure and strain sensors. So this research group actually developed a self-powered and triboelectric all-fiber pressure sensor by an electrospinning technique. This sensor consisted of polyvinylidene fluoride silver nanowires, nanofibrous material as a negative layer, with an ethyl cellulose nanofibrous membrane as a positive layer. This result demonstrates that the sensing mechanism of the pressure is due to the effects of contact electrification and electrostatic induction. The current output of the sensor doesn't show very obvious changes, which shows that the sensor has an excellent stability. It can work in a self-powered manner for detecting and quantifying various human motions on different body parts, which is pretty good. So by placing a piece of an insulated crepe paper between the two layers, you can actually take this and form a capacitive pressure sensor. But when an external pressure is acted, the capacitance increases with the decrease of distance between the conductive membranes. When it is removed, the shape of the sensor will actually return to its original shape due to its stiffness and elasticity. And then a strain sensor was also designed based on carbon nanotubes, cellulose nanocrystal, and electrospun polyurethane membranes through a one-step filtration method. And this sensor can also be applied for full range body motion, which provides an ideal strategy of a bunch of different versatile applications. And then the figure, you can see it is a bit blurry as well. But it's basically, part A is like the makeup of this pressure strain sensor. So you have like your conductive fabric on top and like your substrates and stuff as well. And then figure B to the right just kind of shows what happens when you're like separating or like pushing them together from the strain would be like the contacting. So they're almost hitting each other, but they haven't, like they hit each other, whereas approaching is like they're getting closer, but they haven't actually touched yet. You can go to the next one, please. Thank you. Okay, so now I'm just going to talk about the future outlooks.
Sorry.
You're good. Okay. So cellulosic materials can be made into flexible substrates for different electronic devices through a simple physical process and some chemical modification. But a lot of research and exploration should be done to actually determine the properties that they have, including conductivity, stretchability, and integrability with the skin, muscles, or tissues. The last paper that we actually talked about from September 2020, the researchers actually suggested to perform element replacement, hybridization, self-assembly, and interfacial structure design to actually kind of further quantify what these cellulose-like materials are good for and their overall complete properties. Now you can go to the next one. Okay. So one of the main limitations of the current advancement in these electronic skins is that they currently only exhibit a single function because they lack multifunctional integration. These overall limits their potential applications and ultimately affects the stability of the performance. So to help with this, future research should be like focused on the development of processing conditions to kind of build a whole new generation of flexible electronics that can integrate multiple functions. So some studies have so far kind of contributed to this. In July of 2020, an electronic skin based on a cellulose composite hydrogel with liquid crystal structures and bright colors with multiple responsiveness has actually kind of been developed a little bit, and they refer to it as the chameleon skin. Which is kind of cool because it changes colors based upon different things. But ultimately, we want an electronic skin that is more like an octopus rather than a human because they can do a lot more than what we could because they would ultimately have more available options. So cellulose itself has a high biocompatibility and degradability, but when we're using it in medicine, it's still kind of fairly new. There haven't been too many studies done to further expand upon that. Muscle gels, neuroscience engineering, diagnostics, and implantable microbot devices haven't been investigated yet, but perhaps within the future, like they should be, because they would definitely bring electronic skins like more into fashion and used a lot more. And then if they help improve the biocompatibility or the degradability, they can kind of focus on other aspects of these skins, but definitely this is probably one of the more important things to kind of investigate a bit more and help to improve. So our bodies can actually continually provide thermal energy, which can be harvested by a device and ultimately generate a current. This will provide a plausible solution to power most of the integrated circuits and sensors in these e-skin systems. This is already being done on some watches, such as the Matrix Power Watch. It has a TE generator that uses the body heat to self-charge its internal battery, as well as measure daily activities. But unfortunately, we can't just like take this generator from a watch and throw it into the e-skin because it doesn't meet the skin conformal requirements, which is kind of crucial. A study was actually published in 2019 that talks about the use of body heat to power future e-skins, where they take the same concept, but they liquidize it and inject it into these e-skins to hopefully self-power the system. But with that study, the generator can have two working modes, so it can drive low power sensors and like constantly have them going, or they can accumulate energy to then bring out power the sensors with a higher energy consumption. So if we had the ability to kind of put this more into practice, then we wouldn't really have to worry about like our e-skins going too wrong or like messing up a little bit, because they'll constantly be running and constantly be taking more stuff, as opposed to possibly having to take them off for a little bit and just kind of letting them rest. Okay, so another future hope for these skins is basically to expand on the flexibility. So far they are pretty bendable, but they're still not as stretchable as natural skin. If both the nanogenerators and the sensors are printed onto elastic substrates, the overall thickness of the device will only be a couple of millimeters. This ultimately would allow for a more intimate contact and overall maximum flexibility. So we're hoping sometime in the future they would be able to accomplish this a bit more, which would also just help out with more of the properties of the cellulose-based skins. So another issue with this is degradation. Over time, it does become a huge issue. It can arise from a bunch of different sources, including deformation, environmental conditions, or even external damage. Since these skins are so small, it's actually really hard to detect a crack at an early stage. So you would either have to periodically inspect them, which would honestly just get so annoying and so costly. So it is kind of essential to have materials that can either self-repair or have some sort of self-healing coating to protect the active components from any harmful exposure. They are mostly self-repairing and self-healing right now, but further incorporating that would be good. There are some suggestions saying that ink formulated materials would be the best choice because they enable the integration of power supply and energy storage in the most cost-effective and straightforward way. When looking into developing more of these skins, some characteristics that should be focused on are the sustainability and continuing the use of the biogels within the skin composition. There was a study done back in 2018 to help improve the sustainability, but it talked about doing it in a more green method, like actually literally they used a plant. So plant-based e-skins, they have pollen-based e-skins for elasticity, leaf-based for biocompatibility, or even rose petal e-skins for flexibility. These raw materials are abundant and they're renewable, so the materials would actually never run out. So you could constantly be making these as long as we don't kill off the bees. But using these should ultimately enhance the sustainability and versatility of e-skins, but they haven't really been thoroughly tested. This was kind of just like a one and done research paper. It was never fully expanded on too much. But knowing this is one of the ways to enhance the sustainability of these skins, it would probably be beneficial to perform more studies to decide how much of an impact they will truly have over these biomimetic e-skins. So in conclusion, these electronic skins are still relatively new within the medical field, and they are slowly emerging into other uses such as prosthetics or turning the world into cyborgs. They are beneficial to those who may need it, including those with diseases such as Parkinson's or other paralysis. These biocompatible sensors are good to use for the medical field, as they are able to sense many things, including temperature, blood pressure, or other neurological diseases. When making these electronic skins, cellulose is a good network to consider due to their high aspect ratio and their overall abundancy in nature. With the large amount of research done on these electronic skins, it is shown that there are many advantages, but there are still some things to actually research further, including sustainability and flexibility. And yeah, that's it. So I guess thanks for listening and suffering with us.
Yeah, thanks, guys.
Thank you.
I will stop my sharing.
We'll leave it on, actually.
Okay, yeah, good idea.
So I'm going to open the floor to questions from Susanna and Tamara, reminding them that their participation grades do depend on some questions. And I guess Paul's not getting a participation grade, so he's actually going to lose a good chunk of his percentage mark. Oh, poor Paul. Okay, Samara, go ahead. Do you want to unmute?
Guys, give me a second.
Hello?
Hello? Guys, can you hear me?
Yeah, I can hear
Yeah.
you now.
All right, so it's 3 a.m. I'm just tip-topping around my lunch. Sorry. Okay, so I just have one question. So did you guys read something interesting about how the chemical modification or manipulation had impact on different functionalities? Like Kirsten showed a slide where she showed that how various hydroxyl groups on these cellulose were converted to sulfonic and or hydroxyl, I think, carboxylic, and there was a lot of, yeah, this one. Thank you, Kristen. So did you guys look into anything that these chemical manipulation has some particular functionality application? I hope I'm able to phrase my question fine.
Yeah, well, these particular ones were showing the one on the left, it was supposed to be to enhance hydrophilicity, and the one on the right was supposed to be hydrophobicity. But I did come across a lot of a different work with cellulose skins that that outline different functionalities. I honestly can't remember any off the top of my head, but I guess just from Ashley's reviews here, or the literature reviews. I'm not sure. Ashley, do you know how they manipulated them?
For this one?
For any of them.
For any of them. It didn't really talk about like if they modified or manipulated anything. The one before this is mostly just like dealing with the gel and everything, and then when you're adding the water, it changes around the hydrogen bonds and everything, which changes the mobility and ultimately like affects the actual cellulose like gel in that way. But yeah, it just leads to more like self-healing properties, I guess.
Yeah, so with I remember with this one that it's only built out of cellulose ions and water, right?
Yes.
Okay, yeah. So I guess to answer your question, don't have anything specific for you right now, but I do have quite a few papers on my computer right now that would have different functionalities that were endowed on it. However, I am sharing my screen right now, so I wouldn't be able to.
That's all right. Would you be able to send them to me? I'm really curious. I love that slide that you
definitely.
showed.
Yeah,
That would
definitely.
be great. Thanks, guys. It was a great talk, really. I don't think I have any other question. Yeah, but I'm just wondering, does anybody among you is interested in doing actual research on this topic now in your, I think, undergrad research?
I mean, after doing all the research for this, like my brother is in computer science, so I was like, hey, let's team up and make one. But he said no. But I just think it's really cool, especially like the chameleon one that I read about too. It's just very interesting.
It's an amazing concept. I loved it.
Yeah, no, I definitely am interested in doing research just about bioelectronic materials or biodegradable electronics, for sure. I don't know about e-skins in particular, but yeah.
The chemistry must be neat. It's super. Thanks, guys.
Okay, thank you, Samra.
Good talk.
Hey guys, you can hear me?
Yep.
Great talk. I kind of have a series of questions, mainly based on the sustainability aspect of this. I don't know if you've mentioned it or maybe you just skimmed through it. For Ashley, when you're with the papers, where do they get like the cellulose source?
Some of them are like, a lot of them don't actually say where they're getting them, but I know like we've read about ones that are pulled from like wood and like actual like plants. Like the one that's pulled from the different plants and stuff, it's basically just taken out of like whether it's out of the leaves or whatever and stuff like that. But it doesn't like actually specify where like it's pinpointed to, but I do know that there's a lot like from like the leaves or like the wood of the plant and stuff.
Yeah, for sure. My knowledge on cellulose is kind of limited. I know a little bit about like natural polymers and things like that, and when conducting these experiments, a lot of groups tend to use corn, and then that brings up some issues because that using corn for cellulose may lead to issues with impeding on food sources. And I just think, do you think that would be a problem with these materials?
I think at the moment, I'm not sure research is extensive enough to make a huge dent in our food resources. But I guess, I mean, there's malnutrition throughout the world, so depending on how you look at it, we're already in a food shortage. And I'm not sure that right now the scale that it's at, it would have much of an impact. But I guess if we built all of our materials out of it, we would have to figure out ways, maybe stackable. I think you would just make technology. You would like stackable greenhouses and stuff like that. Apartments of greenhouses that would allow for more food production, which I think increasing food production around the world is kind of a hot topic anyways, so might as well add it for materials. I don't know. Ashley, what do you think? Okay.
I don't really think it's gonna do much right now because this is all still kind of just starting almost, but I don't know, like we are pretty much still in a food shortage like in a lot of places, so I don't really know if using them the whole time would be good. Like you can use them for some of them, but I definitely wouldn't use corn for all of them.
Yeah. I think overall just having that biodegradable aspect for electronics is going to impact the environment in a positive enough light that it might balance out any disadvantages.
Yeah, sorry, that also leads to my next question, where I think you, Ashley, talked about the degradability of it. So in what aspect do you think it is biodegradable if we're using it for like skin and stuff like that? Because can it degrade on us, or like how would that work?
Well, I mean, like it's mostly just like anything that's like any external stuff is really what's going to cause it to actually degrade, like because it's so compatible with our skins right now with all the research. Like our skin isn't going to do anything and it's not actually going to hurt our skin. The one gel, because they've done the studies that show that you should be using the gel with the skin, that gel will actually protect our skin for sure. And when you like, if you have to take it off, it's like completely non-invasive. Like it will not rip off like a single hair on your arm, let's say, because it's just so like it compatible enough that it will stick and it will read, but it is not invasive, so you can take it off without an issue. So like all the degradability is mostly just coming from like the outside forces that they just kind of want to try to eliminate.
Okay, cool. Those are all my questions. Thank you. Great talk.
Thanks. Thanks, Susanna.
So those were good questions. Thanks, Susanna. Sama, do you have anything more, or you're basically trying to stay awake at this point?
I'm pretty awake. I'm just more interested in imagining its potential application. I just love this topic, really.
Okay, I got a few. So just a few comments as well. So I'm like, it's a well put together presentation. Really good use of images. I think there were some points where you're saying this is a text-heavy slide. I agree with that. I think some of them could have been a little less on that. My biggest criticism on that is there were no references anywhere on the slides, which is a bit problematic, especially when you're taking images from papers. So just make sure that you put references on slides if you're taking.
Yeah.
Yeah, okay.
Yeah, it was a bit of a rush to finish. I
No,
was
I
gonna
understand.
add all of them. Yeah.
That's my big sort of tick against you guys on this one. Everything
Okay.
else is it's like, obviously you did a lot of reading on this. So I want to come back to, about the biomaterials side of this, because Kirsten, you really went into a lot of detail on the electronics and the sensing on this. So conceptually, how would you go, like, I can sort of understand how any one of these could be single sensor. How would you go about trying to integrate multiple different feedbacks? Because you're talking about all the different types of nerves that we have in our skin, and all these different nerves have different ranges of recognition. They respond to slightly different tactile interactions.
Yeah.
I really like that they differentiate between, like, obviously it's true, stroking and then sensual stroking. Like that there are two different types of stroking, different nerves.
Yeah.
So
I'll go back to
yeah.
how are we making these densely packed bioarrays?
Yeah. So and I know you're not the one person who needs to solve this problem, but like, conceptually, how would you go about trying to integrate multiple different sensors in here? Because you're talking a lot about the different types of sensors you can use: contact sensors, piezoelectric responses.
Yeah.
But a lot of those come down to you compress it and it gives a response, right?
Yeah.
And so these are all different forms of compression for the modalities, but we get different responses depending on that. Like we sense different things.
Yeah, correct. Yeah, so from what I've read, essentially they're looking to, or some people are looking for these multi-arrays. They're very much in their infancy, so it hasn't been done a lot for these reasons. It is problematic because the skin has this well-layered structure, and that's not so easy with these devices. However, they are looking to mimic these layering structures. I forgot what I was about to say, but all the different signals. Sorry, let's go back to this one. The reason why they can all be transduced and interpreted in different ways is because the input signal is always translated to the same format. I don't know if that you probably already knew that from the slides, but so if you have a transistor, like in all our electronic devices, transistors help us, forgetting the word here, localize, or
Digitize?
no, sorry. What's the word? Eliminate crosstalk between signals. I've separate, yeah, so separate the input from different signals, and then those are amplified. And a ring oscillator is used to put them into this this wave format. So they're all in that format. We can use multiple means for stimulation. And as I'm saying this, I'm kind of forgetting the point of why I'm saying, yeah, the question. So
back to how can you, because the nerves can really judge between, a stroking motion or a flicking motion, or
yeah,
a slicing motion or a cutting sensation or a pressure sensation. And I'm trying to think how, and that's because we have different nerves that handle those different types of things all built in next to each other. So they're all multiple different, and they're qualitatively different signals, right?
Yes.
Whereas these are all, most of the sensors that you're talking were about, like, if you go back a slide, I think.
Yeah.
They're all pressure sensitive, basically. Like they respond to, you put pressure, boom.
Yeah. So actually, if we think about the nerves under our skin, they all really are just pressure sensors. The only difference is their receptive field sizes and their where they're situated in the skin. So like how deep they are. Sorry, something in my throat. So I think that's where the layering of these types of sensors comes in, and then also just adjusting their field sizes, because all of our pain receptors are actually just built off of thermo and mechanoreceptors. So you can sense pain. It's through the combination of different sensors. So
really, really well answered. I agree with you completely. Has anyone done this? Have they been able to layer these at all yet to try and get these kind of difference?
There have been, I think, multifunctional. So yeah, for thermal and pressure sensors together. But I don't think there's been anything with like pain sensation yet, from what I've read. I don't know if Ashley's read anything about that.
Not really for the pain ones either.
Okay, so I'm going to come to Ashley now for a couple of questions. So Ashley, you're sort of covering some of the examples of the bio. I was getting a little concerned versus the biomaterials, and this is just going to be materials electronics talk. So good, thank you. And so a couple of the examples, I guess I'm kind of following up a little bit on where Susanna was going with her questioning, which is, what's the kind of lifetime of these materials on the skin, and how long, like, because our skin is ridiculously robust, right? But even our skin, we turn over regularly and sort of slough it off. So what kind of lifetime are people talking about when they're trying to use these kind of cellulose coatings? And how would that be, like, how is it hooked up to the nervous system to get the signal to people? Like, how are people envisioning doing this kind of thing? And I'm asking you this because you also had the future aspects kind of thing on that. So
that's a good question that I will try to answer, but honestly, I'm not too sure. Like I know a lot of it is basically just like from the receptive signals. So if you're putting like obviously your nervous system is like hooked up to the surface of your skin. So I feel like if you have like that gel attached with the sensor, if you push right onto it anyway, it would still trigger like some sort of response. But like with the lifetime of them, either they don't really talk about like how long you can leave it on or like how long it'll last and stuff like that. It just says that you can remove it and replace it as needed. But I don't think that it will necessarily be like a shorter lifespan. I feel like it would be a longer lifespan based off of like what they've done so far. It might not be the longest. It might be able to go a bit longer if they can improve that degradability aspect. But like for now, I don't think it's going to be like you have to like change one every day or something like that. Like I feel like that's a little bit extensive. But like they don't really go into full detail about that or like how it's like fully connected to the nervous system. It just mostly talks about what I've read so far is like if you put pressure onto it, a lot of them will trigger something and trigger a signal. Some of them will actually change color depending on what skin you get. And it just kind of goes like from there. But like for prosthetics and stuff as well, it just says that they can use the sensors on. So like if you had like a prosthetic leg, like below the knee, if you use that sensor on like the knee, as you're like walking, if you push, when you're pushing down on your prosthetic, it'll push up on the gel and the sensor, which will ultimately send that signal. So you'll feel the pressure of like walking on something again. But like it doesn't really fully go into too much detail on that. I don't know if Kirsten read something about it either, but yeah.
About the lifespan. Well, I guess we just have to keep in mind that usually right now it's being used as more of a structural component, so it's always mixed with different polymers and coatings that will obviously maybe make it less degradable, but more robust in the long run, and definitely increase its lifespan. So
Yeah,
and they haven't.
That's what I was looking for. That's a really good answer. Thank you. Yeah, so at this point, so we're talking about using these things kinds of as prosthetics and biomaterials as prosthetics. So having done all this, biomaterials are sexy for things like this, right? Like the degradability, I really like you guys talking about that. There's this promise of greenness, though I'm a little skeptical. It's just when you're talking, like, a material could be green, but you need to look at the entire lifespan of the material and the processing. And sometimes oil-based materials use less energy to make into a final product than taking it from a plant, and so you
For sure.
screen it that way. But what's your you guys do a little bit of work on this, right? Or at least one of you is working with Simon, or no?
Yep. No, I am. Yep.
Yeah. Good. So, what's your viewpoint on sort of the biomaterials versus other traditional materials? Like, when we're thinking about what's going to get to market first and what's actually going to work, I love biomaterials. I think they're really useful. I'm a big fan. I still feel it's a bit greenwashing on this. And I don't know if that's the sense you guys got doing this, or if you have sort of a counter argument thinking that this actually might be a useful tool down the line.
Well, I might need to think about that for a second, but I guess just off the bat, I guess I'll say that I still have my love goggles on for biomaterials. Unlike you, I just really like the idea of using the energy supplied by the planet to create our own energy.
Yeah.
And obviously, having, I hope, a few more years to live here, I like the idea of making the planet a less polluted, e-waste full space. But I've never really thought about in terms of like the trade-off between functionality and if it's really worth it in the end. So I might just need to think on that for a second. If Ashley, if you have any thoughts on that, I'm just gonna think for a second.
I don't know, like, I'm with you on like the whole like helping the earth kind of stuff, but my mind, I'm not a biochemist. So my mind also doesn't really care about the bio aspect. So for me, it's kind of like I do care about it just on like a personal standpoint, but I'm also all for like whatever's gonna ultimately be more beneficial in the end. It might not necessarily be the most beneficial for the planet, but it might be more beneficial than these bio-related electronic skins. Like it's kind of a toss-up. Like I obviously want to like not cause the earth to completely like burst into flames, but I also like,
that would be impressive if you did that. Solely you.
Just me. But yeah, so it's like, I don't know, it's a tough one.
Yeah, I will say that as we were going further into our research, and I was realizing more and more that cellulose maybe wasn't the ideal material for these purposes. Not even like the ideal biomaterial. If I were to redo this, I probably would have chosen something that had some sort of conductive property. But I guess overall, I just think that if we can get both, then why not? And I don't think that research in these areas is futile or unnecessary.
Okay. What would be a conductive biomaterial?
From what I saw, silk.
Really?
Silk had conductive properties. Yeah, there was a lot of e-skins with silk.
I wonder if silk is just keratin, isn't it?
Yeah, some sort of protein.
I guess the course could have been all about that kind of stuff. Maybe I don't know. Yeah, it is keratin, and maybe it's a really like lots and lots of ionic amino acids on it. That's cool. I was actually thinking lignin is actually probably conductive as well, maybe because it's these
Really?
huge conjugated chains. But good luck trying to
tune it. Yeah.
Cool. Thank you. That good answers to those. Trying to think if there's anything else that's really relevant. So I guess the last thing is just in Ashley's section. I have a real soft spot for carbohydrate hydrogels. I've done quite a bit of work in that, and so I love carbohydrate hydrogels. The problem with carbohydrate hydrogels is they're hydrogels, and so they kind of dry out when you don't want them to. So I don't know if anyone talked about that, like how you would, because it's really cool that you can reversibly tune, I guess. I think it says Turing microstructure. But you can reversibly tune the microstructure through the addition of water. Did they discuss how that could be used practically? Like, would it be sort of to sense humidity? Like, would that be the purpose of this?
It's not really to sense it. More so like it's just kind of giving way to a bit more flexibility aspect. So it's actually going to ultimately take like water from the moisture from the humid air and kind of use that is the way that they were wording it in the paper.
Yeah.
But it didn't really say like ultimately why, other than just to kind of help with the flexibility issues.
Okay. A lot of carbohydrate hydrogels dry out over time in air. Like you need a humidity that's above sort of our standard humidity to keep them moist.
Yeah, this one didn't really have a limit, and it didn't say anything about like having them dry out. So I'm not too sure.
Okay, cool.
It would make sense though.
Cool to see it. That was just neat. I never thought about using, because these get used all the time for 3D bioprinting and for acting as scaffolds for stuff.
Mm-hmm.
I never thought about using them as structural components in a organoelectronic. So that's really neat. Okay, I've got no more questions. You guys have done a good job here. Susanna or Samra, anything else?
No, I think I'm gonna stop grilling them. So
yeah. Okay. Thanks. I guess actually went the entire lecture time. So last class we will spend a little bit of time talking about some cyclic polymers, and then I think we can talk a little bit about maybe we can have a discussion around green chemistry as well. I'm going to sort of, if people want to meet a bit more and talk about green chemistry and we can't get into all that, I'm happy to meet at some point in April. We can sit down and chat because I think it's something important to talk about. But that's fine. It'd be spilling over the course. It'll be completely voluntary. But I want to cover some of the cyclic peptide stuff in the last class. Okay.
Okay, great. Sorry, John, do you want us to send you the presentation and our bibliography?
Yeah, if you can send me the
one
bibliography, that'd be great.
Okay, awesome. Thanks. And Samra, I'll send you the dozens of papers I have on the e-skins.
A bit more work for you two, but
yeah,
you could add the references to your slides before you
definitely
the presentation. Okay. If you could do that, and let's say by Tuesday. If you can me with that, then I'll pretend that they were on there all along.
Okay, thank you. Sorry.
No, it's okay. It's I think, it's one of these. Your slides are beautiful, and the problem with references is they make slides less beautiful. But
true.
like I think with the point of this exercise was partially to sort of have done sort of an in-depth literature search and try and synthesize things together. I think you guys did an absolutely phenomenal job of that. But then it becomes important to actually sort of show that the research is in there. And technically, on a pure technical definition, it's plagiarism to not cite the sources when you're using things like that. So
Yeah.
We always walk this line whenever we're giving presentations at conferences and things over when you're citing and when it's like a Creative Commons image that you don't need to. But in this, yeah, you would definitely need to cite all the way through. Okay, cool.
Okay.
Thank you. That was great.
Thank you. Have a good weekend, guys.
You too.